Tonight, we're stepping into a world that seems silent, but is anything but. Plants that remember being touched. Trees older than human civilization. Roots that reach deeper than skyscrapers, and leaves that float on nothing but trapped air. Some plants bloom only once in a century. Others survive in boiling water, or rebuild themselves from a single broken branch. As you relax, let's explore the hidden intelligence and astonishing survival strategies of the plant kingdom. A world that breathes, senses, and quietly shapes the planet while we sleep beneath its leaves. Hello there, and welcome back to Dreamy Science Stories. Tonight, we're gently turning our attention to the quiet green companions that share our world in silence. The plants that stand rooted beneath the sky, swaying in the breeze, seemingly still and unchanging. Yet behind that calm surface lies a world full of hidden dramas, silent conversations, and astonishing abilities that science is only beginning to uncover. Plants shape the air we breathe, the food we eat, and the landscapes we walk through every day. They create forests, fields, gardens, and jungles, vast living tapestries that stretch across the planet. And in their quiet presence, we often find peace. But their stillness is deceptive. Within their stems, roots, and leaves, life is constantly unfolding. Signals are being sent, defenses are being prepared, memories are being stored. Most of the time, we walk past trees, flowers, and grasses without a second thought. They become scenery, background to the faster, louder lives of animals and people. But plants are anything but background. They sense light, gravity, touch, and even sound. They keep time with internal clocks. They share resources with neighbors. They remember stress and adapt to change. Science is revealing that the plant world is not simple or passive. It is dynamic, responsive, and quietly intelligent in ways that challenge how we think about life itself. So as always, if you enjoy drifting into science and wonder, you can share a thought below or join us again on another journey. But for now, let the noise of the day fade away. Let your body grow still. Breathe slowly, and allow your mind to wander among the hidden lives of plants. Let's begin. Plants communicate with each other using invisible chemical signals. Though plants cannot speak or hear, they are constantly communicating in their own subtle language. When an insect bites into a leaf, the wounded plant releases chemicals into the air, tiny invisible molecules that drift on the breeze. These signals act as warnings, alerting nearby plants that danger is close. The neighboring plants, upon detecting this chemical alarm, begin preparing their defenses. They produce bitter compounds, toxins, or toughened tissues that make them less appealing to hungry insects. In some cases, they even release scents that attract predators of the insects, calling in natural bodyguards. This form of communication isn't limited to a single species. A tree under attack may warn shrubs, grasses, or even unrelated plants nearby. To human eyes, a meadow or forest appears quiet and still. But to the plants, it is alive with invisible messages, a constant chemical conversation passing silently through the air. They are not isolated individuals. They are participants in a shared system of warning and defense, quietly protecting one another in a living network of cooperation. Trees share nutrients through vast underground fungal networks. Beneath the soil, out of sight, forests are connected by intricate webs of fungi that link tree roots together. These networks, sometimes called mycorrhizal networks, act like living pipelines. Through them, trees exchange sugars, minerals, water, and chemical messages. A large, mature tree with access to sunlight can send extra carbon to younger saplings struggling in the shade. Trees weakened by disease or injury may receive nutrients from healthier neighbors. Some studies suggest that trees even recognize their own offspring, sending more resources to genetically related saplings. Scientists have nicknamed this hidden system the Wood Wide Web because it functions much like an underground internet, connecting trees into a cooperative community. Above ground, Each tree appears separate and independent. But below the surface, their roots are intertwined in a constant exchange of life. Every forest you walk through is not just a collection of trees. It is a connected living organism, sharing resources and information in the darkness beneath your feet. Some flowers can generate their own heat. Certain flowers have evolved an extraordinary ability. They can warm themselves. In cold environments, this heat helps attract pollinators and spread scent. The skunk cabbage, for example, can produce enough heat to melt snow around it in early spring. By warming itself, it releases its scent into the cold air, drawing insects that are active earlier than usual. The giant water lily also generates heat during its nighttime bloom, creating a warm refuge for beetles that help pollinate it. Inside its massive petals, insects find warmth and shelter, while the plant secures its chance to reproduce. This heat production requires energy, but the evolutionary reward is enormous. What looks like a fragile flower is, in reality, a tiny biological furnace, manipulating temperature to survive and thrive. Even the quietest blossom may be glowing with hidden warmth in the dark. Roots may use sound-like vibrations to navigate underground. Roots grow in darkness, pushing through soil in search of water and nutrients. But soil is full of obstacles, rocks, dense patches, and other roots. How do roots find their way? Researchers have discovered that growing roots produce faint clicking sounds as they push through soil. These sounds are extremely subtle and require sensitive instruments to detect. Some scientists suggest that roots might sense the vibrations they create, using echoes to navigate their surroundings, almost like a primitive form of sonar. There is evidence that roots can even grow towards specific sound frequencies, hinting that they may be listening to the underground environment in a way we barely understand. What appears to be blind, random growth may actually be a sophisticated exploration strategy. Beneath every tree, every garden, and every field lies a hidden world of roots quietly probing the earth with vibrations, mapping their way through the darkness. Some seeds can remain dormant for thousands of years. Seeds are tiny vessels of time. While most sprout quickly, some can wait for centuries or even millennia before growing. In one remarkable discovery, scientists revived a lotus seed that had been buried for over 1,000 years, and it grew into a healthy plant. In another case, seeds of Arctic flowers frozen in permafrost for tens of thousands of years were brought back to life. Seeds achieve this by entering a state of deep dormancy, shutting down their internal chemistry and sealing their genetic material inside protective shells. They can survive droughts, fires, floods, and even ice ages, waiting patiently for the right moment to awaken. A seed can be older than empires, older than written history, yet still carry the spark of life. It is a quiet promise, preserved through time, waiting for sunlight, water, and warmth to return. The corpse flower smells like death to attract life. The Titanarum, known as the corpse flower, is famous for its towering bloom and powerful stench. When it flowers, it releases an odor that smells remarkably like rotting flesh. To humans, the scent is overwhelming and unpleasant. But to flies and beetles that feed on decaying animals, it is irresistible. The flower even warms itself to mimic the heat of decomposition, making the illusion even more convincing. The bloom is rare and brief, sometimes appearing only once every several years and lasting just a few days. When it does, people travel from around the world to witness it, lining up to experience its strange beauty and infamous smell. For the plant, this is simply strategy. By imitating death, it ensures pollination and life. The corpse flower reminds us that plants can be master manipulators, using illusion and deception to achieve survival. Some trees can clone themselves for tens of thousands of years. Some of the oldest living organisms on Earth are not single trees, but vast colonies of clones. The quaking aspen reproduces by sending underground shoots that sprout new trunks. Each trunk may live for only a century or two, but the root system beneath them can persist for tens of thousands of years, continuously producing new trees. One famous colony called Pando in Utah covers more than 100 acres and is estimated to be around 80,000 years old. What looks like a forest of individual trees is actually a single organism with one shared genetic identity. Clonal colonies blur the line between individual and collective life. They show that what seems like many separate trees may be one ancient being, quietly stretching across time and space, renewing itself again and again. Plants can sense vibrations from insects chewing on their leaves. Plants may not have ears, but they can detect sound-like vibrations. When caterpillars chew on leaves, the vibrations travel through the plant's tissues. Researchers have found that plants can recognize these specific chewing patterns and respond by producing defensive chemicals. Remarkably, plants do not react the same way to wind or random movements. They respond specifically to the unique vibrations caused by insects feeding. Imagine a leaf detecting the rhythm of being eaten and immediately preparing its defenses. It suggests that plants have a finely tuned awareness of their environment, listening through vibrations and responding with precision. Plants may appear silent and unaware, but in reality, they are constantly sensing, reacting, and defending themselves in ways we are only beginning to understand. Stressed plants make strange clicking sounds in silence. When plants experience stress, they don't simply endure in silence. Using highly sensitive microphones, scientists have discovered that plants can produce faint, sharp ultrasonic clicking sounds when they are injured or deprived of water. These sounds exist far beyond the range of human hearing, but when translated into audible frequencies, they form clear, rhythmic pulses. Tomato and tobacco plants, for example, emit far more clicks during drought conditions than when they are healthy and hydrated. It is as if the plant is quietly signaling distress, sending hidden echoes into the surrounding air. The cause of these sounds is still debated. One theory suggests that tiny bubbles form and collapse inside the plant's water transport system, creating miniature pops as the plant struggles to move moisture through its tissues. Other researchers wonder if these clicks might serve as communication signals, perhaps detected by neighboring plants or even insects that rely on plants for survival. Whatever the explanation, the discovery challenges the long-held belief that plants are silent and passive. The green world around us may be filled with invisible acoustic signals, tiny whispers of struggle and survival, constantly unfolding beyond our perception. Some desert plants drink water straight from fog. In deserts where rain is rare and the ground is dry for months or years, plants have evolved astonishing ways to survive. Some species don't rely on rain at all. Instead, they collect water directly from the air. Their leaves, spines, and surfaces are shaped with microscopic textures that trap tiny droplets of fog. As the droplets gather, they merge and trickle downward, guiding precious moisture toward the plant's roots. Even a passing mist can become a life-saving drink. Cacti, succulents, and certain desert shrubs use this technique to harvest dew and fog, turning invisible vapor into usable water. To human eyes, the desert appears lifeless and dry. But to these plants, every breath of humid air is an opportunity. They remind us that even in the harshest landscapes, life adapts in quiet, ingenious ways, sometimes by learning to drink the sky itself. Forests help create rain by releasing water into the sky. Forests are not just passive recipients of rainfall. In many cases, they help create it. Through a process known as transpiration, trees release vast amounts of water vapor through tiny pores in their leaves. This moisture rises into the atmosphere, cools, and condenses into clouds. In dense forests like the Amazon, this process is so powerful that trees essentially generate their own rain systems. Some scientists believe that large-scale deforestation could disrupt these cycles, turning lush regions into dry savannas. When you stand beneath a forest canopy, you are standing beneath a living fountain. Invisible streams of water are rising from leaves into the sky, cycling moisture across continents. Trees do not merely drink the rain. In many ways, they summon it, sustaining ecosystems, climates, and life itself. Some orchids deceive insects by imitating female bees. Certain orchids have perfected deception. Instead of offering nectar, they trick insects into pollinating them by mimicking the scent of female bees. Male bees, drawn by what they believe is a potential mate, approach the flower and attempt to mate with it. During this encounter, pollen sticks to their bodies and is transferred to the next flower they visit. The illusion can be so precise that even experienced insects are fooled. Some orchids go further, shaping their petals to resemble the bodies of female insects, completing the visual and chemical disguise. To humans, the flower may appear simple and delicate, but to the insect world, it is an irresistible illusion. This strategy shows that plants are not passive. They are clever manipulators of perception, exploiting instincts to secure survival, using deception as a tool of life. The largest living organism on Earth may be hidden beneath forests. In the Blue Mountains of Oregon, scientists discovered something extraordinary: a single organism spanning nearly 4 square miles. It is not a whale, not a giant tree, but a fungus known as the honey fungus. Underground, its thread-like filaments weave through the soil, connecting with countless trees. Estimates suggest this organism weighs hundreds of tons and may be thousands of years old. Above ground, it appears only as small clusters of mushrooms scattered across the forest floor. But beneath the surface lies a vast living network quietly feeding, growing, and expanding. It reminds us that the true giants of nature are not always visible. Forests are layered worlds, with ancient organisms stretching across landscapes in silence, unseen beneath the roots of trees. Sunflowers follow the sun in a daily dance. Sunflowers are famous for their ability to track the sun across the sky, a phenomenon known as heliotropism. Young sunflower buds turn their faces from east to west during the day, maximizing their exposure to sunlight. At night, they slowly rotate back to face the dawn, ready to greet the morning light. As they mature, most flowers settle facing east, warming quickly in the morning sun and attracting pollinators. Many other plants also adjust their leaves or flowers to capture optimal light. These movements are slow, nearly invisible to us, but when sped up, they appear like graceful dances, leaves stretching and turning in rhythm with the sky. What seems like stillness is actually continuous motion, guided by sunlight and internal biological clocks. Land plants can be powerful producers of oxygen. We often hear that ocean algae and plankton produce most of Earth's oxygen, and globally this is true. But in many regions, land plants are the dominant source of oxygen. Vast forests, grasslands, and wetlands perform photosynthesis on an enormous scale, transforming carbon dioxide into breathable air. In regions like the Amazon basin, the sheer density of vegetation makes it one of the planet's most important oxygen-generating systems. Every tree, every leaf, every blade of grass contributes to this invisible process. The breath you just took may have been shaped by forests thousands of kilometers away. Plants are not just scenery. They are the lungs of the land, quietly sustaining life with every sunrise. Some plants survive being frozen solid. In the coldest regions of Earth, certain plants endure conditions that would destroy most life. Arctic mosses and alpine species can survive being frozen solid for months. Their cells produce protective sugars and proteins that prevent damaging ice crystals from forming inside. When temperatures rise, they thaw and resume growth almost immediately, as though waking from a long sleep. Some species can survive repeated freeze-thaw cycles without injury, making them some of nature's toughest survivors. Their resilience offers inspiration for scientific research, from preserving crops to protecting human tissues. Though they appear delicate, these plants thrive in places where few others can survive, quietly enduring extremes of cold and darkness. Cacti can live for centuries with almost no water. Cacti are masters of desert survival. With thick, waxy skins and specialized tissues for storing water, many species can survive months or even years without rainfall. Some giant cacti, like the saguaro, can live for more than 200 years, standing through generations of droughts and storms. Their spines reduce water loss and provide shade, while their shallow roots spread wide to capture even the smallest rainfall. Inside, they store water like living reservoirs, expanding and contracting as conditions change. In the desert, they stand as symbols of patience, endurance, and quiet strength. Among the silent sands, cacti wait, holding on to life with remarkable calm. Some plants can glow faintly in the dark. Bioluminescence is rare in plants, but faint natural glows have been observed in fungi associated with plant roots, casting eerie green light across forest floors at night. In recent years, scientists have also engineered plants to glow by introducing genes from bioluminescent organisms. These glowing plants may one day light streets or homes without electricity, turning gardens into living lanterns. Imagine walking through a forest at night, where leaves and flowers emit a soft, otherworldly light. A quiet reminder that life can shine in darkness, even in the most subtle and gentle ways. Some plants glow softly in the darkness. These glowing plants are more than a visual curiosity. One day, they could become natural sources of light, gently illuminating streets, gardens, or homes without the need for electricity. Scientists are already experimenting with plants that emit a soft, steady glow, powered only by their own internal chemistry. Even without genetic engineering, some plant tissues naturally fluoresce under ultraviolet light, revealing hidden veins, patterns, and structures that are invisible during the day. Under special conditions, leaves can shimmer with subtle blues, greens, and purples like living stained glass. Imagine walking through a quiet forest at night, where every leaf gives off a faint, ghostly glow. Trees would appear like lanterns made of living matter, softly lighting winding paths and silent clearings. Though naturally glowing plants are rare, the phenomenon reminds us that life can bend chemistry in beautiful and unexpected ways. What looks ordinary in sunlight may hide a secret shimmer after dark, waiting for the night to reveal its quiet magic. Cherry blossom lotus seeds can awaken after more than 1,000 years. The sacred lotus is more than a symbol of purity and rebirth. It is also a living time capsule. In one extraordinary discovery, scientists recovered a lotus seed from a dried lake bed in China and determined it was more than 1,000 years old. When planted, it sprouted into a healthy, vibrant lotus, as though it had only been waiting for a single season. This incredible longevity is possible because the seed enters a state of near-complete dormancy. Its metabolism slows to almost nothing, and its hard protective shell shields its genetic material from decay. It is, in a sense, suspended animation, a pause button for life itself. For centuries, the seed lay buried in silence while civilizations rose and fell. Yet it preserved the spark of growth, waiting patiently for the right moment. Each lotus flower that blooms from such ancient origins carries a story not just of beauty, but of endurance across time. A reminder that life can wait quietly across the ages. Trees remember drought and adapt their future growth. Trees keep a record of their lives in their rings. Narrow rings mark years of drought, while wider rings tell of plentiful rain. But trees do more than record history. Some appear to remember stress and adjust how they grow in the future. After experiencing drought, many trees change how they manage water and energy. They may grow more slowly, conserve moisture, and alter their internal structures, as if preparing for hardship to return. This physiological memory allows them to adapt based on past experiences, blurring the line between instinct and memory. A tree that has endured scarcity does not simply return to normal. It carries lessons forward, shaping its survival strategy for decades or even centuries. Each trunk in a forest is a living archive, holding stories of storms, droughts, and quiet endurance written in wood and time. Wind-faced plants warn each other when under attack. When insects chew on leaves, the damage does not go unnoticed. Many plants respond by releasing invisible chemical signals into the air, known as volatile organic compounds. These airborne messages drift to nearby plants, warning them of danger. Upon receiving the signal, neighboring plants activate their defenses, producing bitter or toxic chemicals to deter herbivores before they are attacked. Some plants can even distinguish between different threats, releasing one set of chemicals for caterpillars and another for aphids. In effect, plants broadcast distress calls, forming an invisible network of communication across fields and forests. To us, the air seems empty, but in reality, it is filled with chemical conversations, a silent language of survival constantly shaping the fate of plant communities. Seedling some plants launch their seeds like tiny missiles. Not all plants rely on wind or animals to spread their seeds. Some use explosive force. As seed pods dry, they coil with tension like tiny springs. At the slightest touch, they snap open, flinging seeds several meters away. Plants like the squirting cucumber build pressure inside their fruit until it bursts, spraying seeds in a dramatic liquid explosion. These miniature launches may seem small, but they are highly effective. By scattering their offspring far away, plants reduce competition for space and nutrients. To witness one of these seed explosions is to see a hidden drama unfold in an ordinary pod. In the quiet plant world, sudden bursts of energy and motion are always waiting beneath the surface. Waterwave mangrove trees can filter salt from seawater. Mangrove trees thrive in salty coastal waters where most plants would perish. They survive through remarkable adaptations that filter or remove salt. Some species block salt at the roots, allowing only fresh water into their tissues. Others push salt into older leaves that eventually fall away, carrying the salt with them. Some mangroves even excrete salt through tiny pores on their leaves, leaving sparkling crystals on the surface. These abilities allow mangroves to build dense coastal forests that protect shorelines, provide habitats, and support countless species. What seems like an impossible environment becomes home for mangroves. They stand as guardians of coastlines, transforming salty edges of land into thriving ecosystems through quiet biological ingenuity. Carnivorous plants become hunters in nutrient-poor soils. Carnivorous plants have evolved a remarkable strategy to survive in nutrient-poor environments. Instead of relying solely on soil, they capture insects, and sometimes even small animals, to supplement their diet. Pitcher plants form deep, slippery tubes filled with digestive liquid. Insects are lured by bright colors and nectar, slip inside, and cannot escape. Over time, they are broken down and absorbed as nutrients. Some tropical pitchers grow so large they can trap frogs, lizards, or small rodents. These plants blur the line between passive greenery and predator. They show that survival in nature can take unexpected forms, even in the quiet, gentle world of plants. Globe showing America as the Amazon rainforest as Earth's breathing system. The Amazon is often called the lungs of the Earth. Its vast forests produce enormous amounts of oxygen through photosynthesis, sometimes estimated at around 1/5 of the planet's supply. Beyond oxygen, it stores massive amounts of carbon and helps regulate global climate and rainfall. Every towering tree and every understory plant contributes to this planetary cycle. But the Amazon is fragile. Deforestation and climate change threaten to disrupt these systems, with consequences that could ripple across the globe. When we speak of the Amazon, we are not just describing a forest. We are describing a living planetary system, quietly breathing for the world. Grapes plants can taste different depending on the soil. The flavor of plants is shaped not only by genetics, but by the soil beneath them. Grapes grown in different regions develop distinct flavors because of differences in minerals, microbes, and moisture. This concept, known as terroir, means the same plant can taste completely different depending on where it grows. Herbs like basil, mint, and rosemary also vary in aroma and flavor based on soil chemistry. Even vegetables like carrots and potatoes reflect the landscape they come from. Every bite carries the imprint of the earth that nurtured it. Plants are deeply connected to their environments, and their flavors are quiet expressions of soil, climate, and time. Leaves change color, not only in autumn, but under stress. We often associate colorful leaves with autumn, but leaves can change color for many reasons. When stressed by drought, nutrient shortages, or damage, chlorophyll may break down, revealing hidden pigments beneath. Some plants actively produce red and purple pigments called anthocyanins to protect themselves from sunlight or deter herbivores. These stress-induced colors can appear even in summer, making a plant look prematurely autumnal. While beautiful to our eyes, these colors are often signals of struggle. They reveal that plants are constantly adjusting their chemistry, appearance, and survival strategies in response to their environment. A sudden splash of color appearing in a quiet green field might seem like a simple seasonal change. But sometimes it's a subtle message, an early signal that a plant is responding to stress, shifting nutrients, or hidden environmental challenges. Plants may look still and silent, yet they are constantly communicating with their surroundings in ways we are only beginning to understand. Some trees grow to astonishing heights, taller than many skyscrapers built by humans. In the misty forests of California, coast redwoods rise toward the sky like living monuments. The tallest known tree, affectionately named Hyperion, stretches more than 380 feet into the air, higher than a 30-story building. At such heights, the top of the tree experiences a completely different world from its base. The air is thinner, the sunlight more intense, and the winds stronger and more unpredictable. Water must travel upward through trunks wider than city streets, defying gravity through a complex network of microscopic tubes that push the limits of biological engineering. And yet, these giants begin life from seeds no larger than a grain of sand. From something so tiny, a towering forest titan emerges over centuries of quiet growth. Standing beneath a redwood, watching its crown disappear into the fog, feels like gazing at a cathedral built by time itself, a living skyscraper crafted not from steel, but from patience. Not all flowers chase the sun. Some save their beauty for the night. As daylight fades and the world cools, certain flowers slowly open their petals under the stars. Moonflowers, evening primroses, and other nocturnal blooms release powerful fragrances that drift through the quiet air, guiding moths and nighttime pollinators to their nectar. Their pale petals glow softly in moonlight, creating ghostly shapes in the darkness. By blooming at night, these flowers avoid competition with daytime plants and take advantage of creatures that only emerge after sunset. To us, a flower opening beneath a star-filled sky feels magical. To the plant, it is a carefully timed survival strategy, proof that nature follows many rhythms, not just the cycle of daylight. In swamps and flooded forests, some trees breathe in ways that seem impossible. When soil is saturated with water, oxygen becomes scarce, making it difficult for roots to survive. To solve this, mangroves and bald cypress trees grow aerial roots that rise above the water like snorkels. These structures, called pneumatophores, pull oxygen directly from the air, allowing the tree to survive where most plants would suffocate. In these strange landscapes, roots stretch upward while trunks stand in water, blurring the boundary between land and sea. These trees remind us that life can adapt in extraordinary ways, reshaping even its most basic structures to endure the harshest environments. Some seeds travel not by wind or water, but by hitchhiking on animals. Tiny hooks, barbs, and sticky hairs allow seeds to cling to fur, feathers, or even human clothing. As animals move through forests and fields, they unknowingly carry these seeds for miles before they fall and take root in new soil. This simple yet brilliant strategy spreads plant life far beyond the parent plant, increasing the chances of survival. In fact, the invention of Velcro was inspired by observing these hooked seeds under a microscope. What feels like an annoying burr stuck to your sock is actually a masterpiece of evolution, a tiny traveler on a silent journey across the landscape. Other seeds embark on even longer voyages across the oceans. Coconuts are famous for their ability to float for thousands of miles, protected by tough waterproof shells that keep the seed alive. Ocean currents become invisible highways, carrying these seeds to distant shores where they can sprout and form entire forests. Mangroves and other coastal plants use similar strategies, sending their offspring across seas to colonize new islands. Every coconut tree on a tropical beach is evidence of an incredible journey, a seed that crossed an ocean, carrying the blueprint for life inside its shell. Some plants move when touched. The sensitive plant, Mimosa pudica, folds its leaves instantly when brushed, as if startled by your presence. Within minutes, the leaves slowly reopen, returning to their original shape. This rapid movement is powered by changes in water pressure inside specialized cells, acting like tiny hydraulic systems. The motion may help deter herbivores or prevent damage. Watching a plant respond so quickly challenges our assumptions about plant life. It feels almost as though the plant is aware, reacting, sensing, responding. In the quiet world of greenery, perception may exist in forms we barely recognize. Some plants can even count. The Venus flytrap does not close its trap after just one touch. It waits for 2 touches within a short time frame before snapping shut, ensuring it captures real prey, rather than wasting energy on raindrops or debris. This ability to measure stimuli and time events reveals an unexpected level of information processing. Once the trap closes, further touches trigger digestive enzymes, slowly breaking down the captured insect. This tiny plant behaves like a predator, blurring the line between plant and animal, and reminding us that intelligence in nature can appear in surprising places. Long before flowers colored the world, ferns ruled the earth. During ancient periods, vast forests of giant ferns dominated the landscape, shaping the planet's atmosphere and contributing to the coal deposits we mine today. These plants thrived in warm, humid climates, spreading across continents before flowering plants ever evolved. Even today, ferns remain incredibly resilient, growing in rainforests, deserts, and even cracks in city sidewalks. When you see a fern, you are looking at a survivor, a living relic from a world that existed hundreds of millions of years ago. Pine cones are quiet sensors of the weather. In dry conditions, their scales open, releasing seeds into the wind. When humidity rises, the scales close tightly, protecting the seeds from moisture. This movement requires no muscles or nerves. It is built into the structure of the cone itself, responding naturally to changes in moisture. Some cones open and close repeatedly as the weather shifts, acting like living barometers on the forest floor. Even indoors, a pine cone may open or close depending on the air in your home, silently responding to its environment. And some trees bleed red. When cut, certain species release bright crimson sap that looks eerily like blood. The dragon's blood tree and bloodwood tree produce this vivid resin as a defense and healing mechanism. Seeing a tree bleed can feel unsettling, but it is simply another reminder that plants, like animals, have complex systems for survival and repair. For centuries, this deep crimson sap has been harvested and treasured by humans. It has been used as dye for fabrics, pigments for art, traditional medicines, and even in sacred rituals. Part of its value comes from its usefulness, but much of its allure comes from its unsettling beauty. To see a tree release scarlet liquid feels strangely emotional, almost as if the plant kingdom were mirroring animal life. But this dramatic resin is simply a sophisticated defense system, sealing wounds and protecting the tree from insects, fungi, and bacteria. Still, the resemblance is uncanny. These trees carry an air of legend and mystery, as if they belong to an ancient myth rather than a modern forest. Standing beneath their twisted branches, watching red droplets fall onto the soil, it's easy to feel as though you've stepped into a storybook world, a place where plants guard their secrets with theatrical elegance. Botanical definitions often defy common sense. Take bananas and strawberries, for example. Despite their names and appearances, bananas are technically berries, while strawberries are not. In scientific terms, a true berry develops from a single flower with one ovary, and its seeds are embedded within the flesh. By this definition, bananas qualify perfectly. Strawberries, on the other hand, develop from multiple ovaries, making them aggregate fruits. Their seeds sit on the outside, each one a tiny fruit of its own. Tomatoes, kiwis, and grapes also fall into the berry category, even though we rarely think of them that way. These surprising classifications reveal how nature doesn't follow human intuition. The next time you peel a banana, you're holding a botanical berry in your hand. And the strawberries in your bowl, despite their name, belong to an entirely different botanical family. It's a gentle reminder that the natural world constantly rewrites our assumptions. Some plants use chemistry to shape their environment. Caffeine isn't just a human stimulant. It's also a powerful ecological tool. Coffee and cacao plants release caffeine into the soil through their leaves and roots, suppressing the growth of nearby competing plants. This phenomenon, known as allelopathy, gives caffeine-producing plants more access to sunlight, water, and nutrients. Caffeine also affects insects, interfering with their nervous systems and acting as a mild natural pesticide. In essence, these plants use caffeine as both a weapon and a strategic advantage in crowded ecosystems. It's fascinating that humans later adopted this molecule for morning energy and late-night focus. For the plant, caffeine was never about productivity or pleasure. It was about survival, quietly manipulating its surroundings with invisible chemistry. Bamboo is one of the fastest-growing plants on Earth. Under ideal conditions, some species can grow nearly a meter in a single day. Instead of building new cells slowly, bamboo stretches specialized tissues at remarkable speed, allowing it to surge upward almost overnight. In many cultures, bamboo is an essential resource for building homes, tools, furniture, and even food. Its rapid growth makes it one of the most renewable natural materials available. After rain, bamboo shoots can appear so quickly that it feels like the earth itself is rising. Although it looks like a tree, bamboo is actually a giant grass, one that grows with astonishing determination. Its relentless upward drive is a testament to nature's ability to adapt, expand, and thrive. In the harshest deserts, some flowers bloom only once in decades. They wait quietly as seeds, buried in dry soil, sometimes for generations. When rare rains finally arrive, these deserts explode into color. In Chile's Atacama Desert, this transformation is known as the flowering desert, where millions of blooms blanket the landscape in vibrant mosaics. These flowers live briefly, sometimes only weeks, before fading back into dormancy. For the plants, this strategy conserves energy until survival is most likely. For humans, witnessing such an event feels miraculous, like watching a hidden world awaken. Even in places that appear lifeless, beauty lies dormant, waiting patiently for the right moment to emerge. Some plants can recognize their own relatives. Studies suggest that certain species grow differently when surrounded by family versus strangers. Among relatives, they may grow less aggressively, sharing resources more evenly. Among strangers, they compete fiercely, growing taller, spreading roots wider, and producing stronger chemical defenses. How plants recognize kin is still a mystery. It may involve chemical signals in the soil, subtle differences in light reflection, or unknown biological cues. Whatever the mechanism, the behavior suggests a surprising level of discrimination and social strategy. Even in silent green communities, cooperation and competition exist side by side. For many trees, fire is not the end. It is part of the life cycle. Eucalyptus, sequoias, and certain oaks have thick bark that shields their inner tissues from flames. Others store dormant buds beneath their bark or underground, ready to sprout after a fire passes. Some seeds even require heat to germinate, using fire to crack open their shells. Flames clear away competing plants, recycle nutrients, and create space for new growth. Walking through a burned forest and seeing fresh green shoots rising from blackened trunks is a powerful sight. These trees don't just survive destruction, they incorporate it into their survival strategy. In fire, they find renewal. In flooded environments, some roots grow upward instead of downward. These aerial roots, called nematophores, rise above the soil to absorb oxygen directly from the air. Mangroves create dense forests of breathing roots, each one essential for survival in oxygen-poor mud. Bald cypress trees form distinctive knees around their trunks, serving a similar function. What looks like twisted wood rising from the ground is actually an elegant solution to a hidden problem. In waterlogged worlds, survival depends on learning how to breathe differently. Leaves are covered in microscopic pores called stomata. These tiny openings act like mouths, letting carbon dioxide in for photosynthesis while releasing oxygen and water vapor. Stomata respond to light, humidity, and internal chemical signals, opening and closing to balance hydration and temperature. Without them, plants could not sustain photosynthesis, and life on Earth would be impossible as we know it. Every breath you take is connected to these invisible pores scattered across billions of leaves. The planet's atmosphere is shaped by countless microscopic openings, quietly working day and night. Some plants launch pollen explosively. Pollination is not always gentle. Certain orchids and flowering plants use spring-loaded mechanisms to catapult pollen onto visiting insects. Others build tension in their structures until the slightest touch releases a burst of pollen into the air. This dramatic strategy ensures pollen sticks to pollinators before they can escape. Nature, even in its quiet floral forms, can be surprisingly dynamic and forceful. To a bee or moth, the experience must feel sudden and surprising. One moment, the flower is still and calm, swaying gently in the breeze. The next, it releases a burst of pollen like a tiny biological launcher. For the plant, this is not chaos. It is precision engineering. Every movement is timed, every mechanism tuned to maximize the chance of reproduction. What we see as quiet, decorative blossoms often conceal intricate structures coiled with stored energy, waiting for the perfect instant to release their cargo. Even in their stillness, flowers are machines of motion and timing, silent engineers orchestrating life in microscopic bursts of action. Orchids are famous for their beauty, but their seeds are even more astonishing. Each orchid seed is so small that it looks like dust floating in sunlight. Unlike most seeds, these tiny grains contain almost no stored food. Instead, orchids rely on a hidden partnership with fungi in the soil. These fungi provide nutrients, allowing the seed to germinate and grow. In exchange, the orchid eventually supports the fungi in return, forming a delicate biological alliance. By producing thousands or even millions of dust-like seeds, orchids scatter their future on the wind, trusting chance and symbiosis. Their microscopic size allows them to travel across continents, settling in distant forests, cliffs, or treetops. To the naked eye, an orchid seed is almost invisible. Yet within that speck lies the potential for one of the most intricate and elegant flowers on Earth. It is a strategy built on extremes, tiny seeds, vast numbers, and reliance on unseen allies. A reminder that nature often thrives not through certainty, but through probability and partnership. In cold climates, most trees shed their leaves and retreat into dormancy. But evergreens have evolved a different solution. Pines, spruces, and firs produce special antifreeze proteins that prevent ice crystals from forming inside their cells. Their needle-like leaves reduce water loss, and their waxy coatings protect against harsh winds and freezing temperatures. By keeping their leaves year-round, these trees can photosynthesize whenever light is available, even during winter. Dark green needles against white snow have become a symbol of endurance and resilience. Behind this endurance lies chemistry, refined over millions of years, allowing cells to resist freezing damage. Every evergreen forest is a living laboratory of survival, demonstrating how life can bend physical limits and remain active in the coldest conditions. Photosynthesis, the process that fuels almost all life on Earth, originated more than 2 billion years ago. Ancient microbes and early plants learned to capture sunlight and convert carbon dioxide and water into sugar and oxygen. This innovation transformed the planet. Before photosynthesis, Earth's atmosphere contained little oxygen. Afterward, oxygen accumulated, enabling the evolution of animals, complex ecosystems, and eventually humans. Every breath you take traces back to that ancient biochemical breakthrough. Today, photosynthesis continues in leaves, algae, and microscopic cyanobacteria, silently sustaining the global balance of air and energy. A simple patch of green grass is part of the same planetary engine that reshaped Earth's history. Plants did not merely adapt to the world, they reinvented it. Deep within the Amazon rainforest, trees and plants release vast clouds of fragrant chemicals into the air. These volatile compounds can repel insects, attract pollinators, and protect leaves from heat and sunlight. Together, they create the rainforest's signature scent, a layered, invisible perfume rising from the canopy. But these chemicals do more than smell pleasant. They interact with particles in the atmosphere, influencing cloud formation and even rainfall patterns. In this way, the Amazon doesn't just produce oxygen, it actively shapes weather and climate. Standing in such a forest, surrounded by invisible chemical plumes, you begin to realize that plants are not passive organisms. They are engineers of air and water, quietly sculpting the environment around them. Vines live in a constant race toward light. Instead of growing tall trunks, they climb using delicate tendrils that reach out and explore their surroundings. These tendrils sway until they touch a surface. Once contact is made, growth changes direction, curling tightly around the support. Some vines can even sense textures, preferring rough surfaces that provide better grip. To us, it looks like a gentle embrace. But for the vine, it is a strategic ascent towards sunlight. Watching a tendril slowly coil around a branch feels like watching touch translated into growth. A quiet form of exploration in the plant world. An oak tree is far more than a single organism. It is a living city. Its branches shelter birds, squirrels, insects, and countless other creatures. Its bark hosts mosses, fungi, lichens, and microorganisms. Underground, its roots connect to vast fungal networks that exchange nutrients and information. A mature oak can support thousands of species at once. Every season brings new life, flowers for pollinators, acorns for animals, falling leaves that enrich the soil. Oaks are foundation species, holding entire ecosystems together. To stand beneath one is to stand beneath centuries of interconnected life. Protecting an oak means protecting an entire community woven into its wood and leaves. Some plants have evolved translucent or even transparent leaves. These leaves act like natural windows, allowing sunlight to penetrate deep into the plant. In deserts, window plants like lithops keep most of their bodies buried underground, exposing only clear leaf tips. Light enters through these windows, reaching photosynthetic tissues safely hidden from heat and predators. In dense forests, similar adaptations help plants capture scarce light beneath the canopy. Transparent leaves blur the boundary between plant and crystal, transforming sunlight into a glowing internal resource. Even the structure of a leaf can be a sophisticated survival technology. Trees in cities live fast and die young. Urban environments offer higher carbon dioxide levels, warmer temperatures, and irrigation, causing trees to grow faster than their wild counterparts. But pollution, compacted soil, heat stress, and limited space shorten their lives. A city tree may survive only decades, while the same species in a forest could live for centuries. Despite this, urban trees cool streets, filter air, and provide habitat for wildlife. They are quiet allies in human landscapes, working tirelessly to improve city life. Their short lifespans reflect the trade-offs of living in environments shaped by humans, speed replacing longevity. Inside every leaf, water flows through microscopic tubes. As it moves, it creates tiny electrical charges, forming faint electric fields around the leaf. Bees can sense these fields. They use them to determine whether a flower has recently been visited and whether nectar is available. In this way, plants communicate with pollinators using invisible electricity. The forest is not only alive with sound and scent, but also with silent electric whispers. A leaf is not just a green surface. It is a living circuit, broadcasting subtle signals into the air, guiding insects, shaping ecosystems, and connecting physics with biology in ways we are only beginning to understand. In every leaf, water, light, and electricity weave together, forming a silent language written in fields, charges, and flowing currents. A leaf is not just a passive surface catching sunlight. It is a living network where physics and biology merge, where invisible forces move through veins of green tissue, translating sunlight and water into life. Each droplet and each photon becomes part of a quiet conversation that has been unfolding for billions of years across the planet. In deserts, survival depends on holding on to water whenever it appears. Many plants have evolved thickened stems, trunks, and roots that act as living reservoirs, storing precious moisture for the long months of drought. Cacti expand like sponges after rainfall, their tissues swelling with stored liquid that can sustain them through scorching heat. Massive trees like the baobab can hold thousands of liters of water inside their trunks, turning themselves into towering natural cisterns. Beneath the surface, certain desert plants grow enormous tubers, underground vaults filled with life-sustaining reserves. These adaptations allow plants to remain green and alive when everything else has turned to dust. For humans, these hidden reservoirs have sometimes meant survival as well, providing emergency water in harsh landscapes. Every swollen stem and buried root tells a story of patience, foresight, and endurance, a living bank of droplets saved for the future. Hidden in the forests of Southeast Asia, the Rafflesia flower emerges like a vision from another world. With petals that can stretch more than 3 feet across, it ranks among the largest flowers ever to bloom on Earth. Its mottled red surface resembles raw flesh, and its powerful odor, often compared to rotting meat, attracts flies that serve as its pollinators. Unlike most plants, Rafflesia has no leaves, stems, or roots of its own. It lives entirely inside its host vine, siphoning nutrients until it bursts forth in a dramatic, colossal bloom. The flower appears rarely and lasts only a short time, sometimes emerging once every several years. To encounter it in the wild is unforgettable. A massive bloom larger than a dining table, smelling of decay, yet fulfilling the simple biological purpose of reproduction. Rafflesia reminds us that plants can be as strange, theatrical, and alien as any creature, challenging our assumptions of what a flower should be. Mosses are among the quiet champions of survival. Some species can dry out almost completely, losing nearly all their water and entering a state of suspended life. In this desiccated condition, their metabolism slows to a near standstill, like a biological pause button. Years later, when rain finally returns, they awaken within hours, unfurling and turning green once again. Special protective sugars and proteins shield their cells during dehydration, preventing damage and allowing revival. These resilient mosses colonize some of the harshest environments imaginable: bare rock, deserts, rooftops, and the surfaces of ancient ruins. They are pioneers, preparing the ground for other life to follow. Watching a patch of moss revive after rain is like witnessing resurrection on a miniature scale, a reminder that life's greatest endurance often hides in the smallest and quietest forms. Recent studies using laser scanners have revealed that trees may sleep at night. As darkness falls, branches and leaves droop slightly, then rise again with the morning light. The movement is subtle, just a few centimeters, but consistent across many species. Scientists believe this nightly shift may help conserve energy, reset internal water systems, or reflect circadian rhythms similar to those in animals. Imagine an entire forest gently lowering itself as night deepens, then lifting again to greet the dawn. While we sleep, trees quietly follow their own rhythms, participating in a planetary cycle of rest and renewal. After a volcanic eruption, the land may appear lifeless, a field of ash and hardened lava. Yet within years, plants begin to reclaim the barren terrain. Pioneer species like lichens, mosses, ferns, and hardy grasses break down rock and enrich the soil, paving the way for forests to return. In places like Hawaii, haya trees are among the first to colonize fresh lava flows, their red flowers blooming against black stone. Volcanic soils eventually become some of the most fertile on Earth. Plants thriving in these landscapes show that destruction can be the beginning of creation. From fire and rock, gardens rise. For many plants, sex is not fixed for life. Some species can switch between male and female, depending on environmental conditions. When resources are scarce, a plant might produce only pollen, conserving energy by avoiding the cost of producing seeds. When conditions improve, it may shift to producing fruit and seeds again. This flexibility increases survival and reproductive success in unpredictable environments. In plants, identity is not rigid, it is adaptive, responsive, and strategic. Nature writes survival into flexibility. The manchineel tree, found in the Caribbean and Central America, looks deceptively inviting. Its glossy leaves and apple-like fruits appear harmless, even appealing. But nearly every part of the tree is dangerously toxic. Its sap can cause blistering burns on skin, and even rainwater dripping from its leaves can be harmful. Burning its wood releases toxic fumes that can damage lungs. Despite its danger, the manchineel stabilizes coastlines and provides shelter for wildlife. It is a reminder that beauty and danger often coexist in nature, hidden behind a peaceful appearance. Grasslands once covered more than a third of Earth's land surface. Vast prairies, savannas, and steppes supported enormous herds of animals and countless ecosystems. Although many grasslands have been converted to farms or cities, they remain vital. Their deep roots store vast amounts of carbon, stabilize soil, and regulate water cycles. Grasses may seem humble, but they have shaped the planet in profound ways. Life does not always grow tall and dramatic. Sometimes it spreads low and wide, forming a living skin across continents. Before synthetic materials, humans relied on plants for rubber. The para rubber tree produces latex, a milky sap that becomes elastic and durable when processed. Other plants, including dandelions and guayuli, also produce latex, offering alternative sources of rubber. For plants, latex is a defense mechanism, sealing wounds and deterring insects with sticky or toxic compounds. For humans, latex became the foundation of entire industries. A simple drop of milky sap connects plant survival strategies to global technology and medicine. Amber, The fossilized resin of ancient trees often preserves insects, leaves, and fragments of prehistoric life. But it can also trap tiny bubbles of ancient air, sealed for millions of years. These microscopic time capsules allow scientists to analyze the composition of Earth's ancient atmosphere. Each bubble is a breath from deep time, preserved in golden stone, carrying secrets from worlds long gone. Amber is not just a fossil. It is a message from ancient forests, whispering stories of climates, creatures, and atmospheres that shape the world we inhabit today. Scientists can even estimate how much oxygen and carbon dioxide filled the air when dinosaurs walked the Earth. By studying tiny bubbles trapped inside ancient amber, researchers can reconstruct the atmosphere of deep time. It's astonishing to realize that a tree, simply by releasing sticky resin, created a natural archive of the very air of vanished worlds. Each piece of amber is far more than a glowing gemstone. It is a frozen breath from prehistoric forests, sealed in golden light, carrying silent messages from ecosystems that disappeared long before humans ever existed. When we hold amber in our hands, we are touching a fragment of ancient sky, preserved by trees that quietly recorded history without ever knowing it. Some aquatic plants have leaves that repel water completely, creating surfaces that seem almost enchanted. Water lilies and lotus plants display leaves where droplets gather into perfect spheres and roll away effortlessly, leaving the surface untouched and dry. This effect, known as the lotus effect, comes from microscopic structures that prevent water from spreading. As droplets move across the leaf, they also pick up dust and dirt, keeping the surface remarkably clean. This adaptation protects the plant from fungal infections and ensures sunlight reaches the photosynthetic tissues below. Human engineers have copied this design to create water-repellent coatings and self-cleaning materials. What looks like a simple visual trick is actually a sophisticated survival strategy. A single leaf shimmering with crystal-clear droplets reveals how physics and biology merge in silent harmony, turning floating plants into masterpieces of natural engineering. Certain flowers have evolved astonishing mechanisms to launch insects into the air during pollination. In these plants, pollination is anything but passive. The mountain laurel, for example, uses petals that act like tiny spring-loaded catapults. When an insect lands on the flower, the petals snap forward, flinging the insect into the air while covering it in pollen. Startled but unharmed, the insect carries the pollen to another bloom. Other species use similar mechanisms, storing energy in their petals and releasing it at the perfect moment. Beneath their delicate appearance, these flowers hide intricate biological machinery. Pollination becomes a dramatic event, part cooperation and part surprise. Plants may not chase pollinators like animals chase prey, but in sudden bursts of motion, they ensure reproduction continues with precision and flair. Some fungi and plants share light energy in rare and surprising forms of symbiosis. While most plant-fungus partnerships involve nutrient exchange from the soil, scientists have discovered cases where fungi can capture light and transfer some of that energy to their plant hosts. In return, the plant provides sugars the fungi cannot produce themselves. This unusual collaboration expands our understanding of photosynthesis, turning two distinct organisms into joint solar collectors. The discovery is still new, and researchers are exploring how common this phenomenon might be. It blurs the boundaries between plant and fungus, revealing that life often operates in partnerships more complex than we imagined. In some ecosystems, the green world does not work alone. It works with invisible partners, merging abilities to thrive in environments where cooperation becomes the ultimate survival strategy. Bamboo forests can reduce noise pollution, acting like living sound barriers. The dense, hollow stalks of bamboo scatter and absorb sound waves, softening the noise from roads, cities, and human activity. When planted in thick groves, bamboo can significantly reduce sound levels, making it valuable in urban planning. Beyond their acoustic benefits, bamboo forests stabilize soil, prevent erosion, and provide habitat for countless animals and insects. Standing inside a bamboo grove feels like stepping into a quiet sanctuary, where outside sounds fade into a gentle hush. Plants shape not only the visual landscape, but also the soundscape of our world. Bamboo does not just grow, it transforms environments, creating pockets of calm in an increasingly noisy planet. Some seeds can only germinate after passing through an animal's digestive system. For these plants, survival depends on a remarkable journey. Their seeds are designed to be eaten, traveling unharmed through stomachs and intestines before being deposited far from the parent plant. Along the way, acids and enzymes soften the tough seed coat, preparing it to sprout. This process, known as endozookery, spreads seeds across vast distances, often delivering them in nutrient-rich droppings. Many fruits evolved specifically to attract animals, offering sweetness and color in exchange for transportation. To us, fruit is food. To plants, it is a ticket to new territory, a way to colonize distant landscapes using animals as living vehicles in a partnership that has shaped ecosystems for millions of years. Ancient trees once grew near the South Pole, where today only ice and snow remain. Millions of years ago, Antarctica was covered in forests filled with towering trees and diverse ecosystems. Fossil evidence shows that relatives of modern conifers thrived in polar regions, enduring months of darkness and months of constant daylight. These forests likely supported complex ecosystems where dinosaurs walked beneath the canopy. As Earth's climate shifted, ice replaced greenery, and the forests vanished, leaving only fossilized traces behind. To study these remains is to glimpse a world completely transformed. Antarctica, now a frozen desert, was once a thriving green continent. This discovery reminds us that Earth is constantly changing, and landscapes we consider permanent have undergone dramatic transformations over deep time. Some plants produce fruits so toxic they can kill large animals. Not all fruits are meant to be eaten. Some are powerful defenses disguised as tempting food. The pom-pom tree in Southeast Asia produces large fruits filled with deadly compounds. The strychnine tree bears seeds containing one of the most famous poisons in history. These toxic fruits ensure that only specialized animals can eat them safely, while most creatures learn to stay away. For other plants, the toxicity is simply a deterrent, preventing overconsumption. To humans, fruit usually means sweetness and nourishment. In nature, fruit can be a lure, a trap, or a warning. Toxic fruits remind us that beauty often hides danger, and that chemical defenses can be as effective as claws or teeth in the silent evolutionary arms race. Leaves can change their angle to avoid overheating in intense sunlight. Leaves are not passive solar panels. Many plants actively adjust their orientation throughout the day to manage heat and water loss. In harsh sunlight, leaves may tilt or droop, reducing direct exposure and preventing overheating. Some plants, like the prayer plant, move their leaves daily, lifting them at night and lowering them during the day. This constant adjustment helps balance light absorption and water conservation. When viewed in time-lapse, a forest canopy appears alive with slow, graceful movement. Each leaf is making tiny decisions, balancing energy and survival. A forest is not a static roof of green, but a dynamic system, continuously shifting in response to the sun. Some plants can detect gravity and always grow roots downward, even in complete darkness. Inside plant cells are tiny dense particles called statoliths that settle in response to gravity, telling the plant which way is down. Roots grow toward gravity, while shoots grow away from it, ensuring proper orientation. This process, known as gravitropism, guides seedlings through soil and air with remarkable precision. Without it, plants would struggle to anchor themselves or find light and water. Beneath the surface, roots constantly sense their position relative to Earth's gravitational pull. Plants are not blind wanderers. They are navigators, guided by invisible forces that shape every movement from germination to maturity. Certain trees can keep a record of lightning strikes in their growth rings. When lightning hits a tree, the intense heat and electrical energy damage tissues beneath the bark, leaving scars that affect how the tree grows. Over time, these scars become embedded in the tree's rings, preserving a silent record of the event. By studying these patterns, scientists can learn about past storms and environmental conditions. A tree struck by lightning carries the memory of that moment for decades or even centuries, etched into its structure. In this way, trees are living archives, recording not only climate and growth but also dramatic events that shape their lives. As the tree continues to grow year after year, it adds new rings around its trunk, and the scars from lightning remain locked inside these layers forever. Even centuries later, these marks are still visible in cross-sections of the wood. Dendrochronologists, scientists who study tree rings, can identify these lightning scars and reconstruct the history of storms that once swept through a region. Some remarkable trees survive multiple strikes, carrying several scars within their trunks like medals from past battles with the sky. Standing in a forest, it is easy to see only bark and leaves, never realizing the stories hidden beneath. Every tree trunk may contain records of fire, drought, floods, and lightning, preserved in silent concentric rings. Trees are not just silent witnesses to time. They are living archives, storing memories of weather, climate, and sky in layers of wood that quietly grow with each passing year. Grass can release a distinctive smell when cut, and that familiar fresh scent is actually a signal of distress. When grass blades are damaged, they release chemicals called green leaf volatiles into the air. These compounds help defend the plant by deterring herbivores and even attracting predators that feed on the insects attacking it. They can also act as warning signals, prompting nearby plants to strengthen their own defenses. To humans, the smell is nostalgic and pleasant, evoking images of summer lawns and open fields. But for the grass, it is a chemical cry for help, a message carried invisibly on the wind. What we experience as refreshing fragrance is actually an alarm system written in scent, reminding us that plants are constantly communicating in ways we rarely perceive. Some desert plants reflect sunlight using silvery hairs that coat their leaves and stems. In the intense heat of arid deserts, these fine hairs act like tiny mirrors, bouncing sunlight away and reducing heat absorption. They also trap a thin layer of cooler air near the leaf surface, creating insulation that protects delicate tissues. Plants like sagebrush and desert lavender appear pale or shimmering under the sun, their silvery surfaces giving deserts an almost otherworldly glow. This adaptation reduces water loss and prevents overheating, both essential for survival where moisture is scarce. To us, the silvery shimmer looks beautiful and mysterious. To the plant, it is a life-saving shield, a microscopic suit of armor designed to endure some of the harshest conditions on Earth. There are plants that produce edible roots so massive they can weigh hundreds of pounds. Beneath the soil, some plants store enormous reserves of energy in swollen roots and tubers. Crops like yams and cassava can grow to astonishing sizes, with giant yams in parts of Africa reaching weights of several hundred pounds. These underground giants serve as survival banks for the plant, storing starch to survive droughts and seasonal changes. For humans, they have become vital food sources, sustaining entire communities for generations. Digging up such a root can feel like uncovering a buried treasure, a dense reservoir of nourishment hidden in the earth. These plants demonstrate how life prepares for uncertainty, storing energy underground not only for survival, but also to feed countless people around the world. Trees can release chemicals that suppress the growth of nearby competitors, engaging in invisible chemical warfare. This process, called allelopathy, allows certain trees to dominate their surroundings by releasing compounds into the soil that inhibit other plants. Black walnut trees, for example, produce juglone, a chemical that prevents many species from growing nearby. For the walnut, this ensures more water, nutrients, and space. For neighboring plants, it can be a silent death sentence. These chemical interactions shape entire ecosystems, determining which plants thrive and which disappear. A peaceful-looking forest is often a battlefield of invisible toxins and competition. Even in stillness, plants are locked in a struggle for survival, using chemistry as their primary weapon. Some flowers bloom only once in a human lifetime, saving their energy for decades before a final spectacular display. The century plant, Agave americana, can spend many years gathering energy in its thick leaves. When the time is right, it sends up a towering flower stalk that can rise more than 20 feet, covered in blossoms. After this single dramatic bloom, the plant dies, leaving seeds or offspring to continue its lineage. Certain bamboos follow similar strategies, blooming only once in decades or even centuries, often synchronizing their flowering across vast regions. Witnessing such an event is rare and unforgettable, a brief moment in a plant's long, secret timeline. These life cycles remind us that nature operates on timescales far beyond our own, where patience and timing are woven into survival strategies spanning generations. Mosses were among the first pioneers to colonize land hundreds of millions of years ago. Early Earth's continents were barren rock, exposed to wind, rain, and sunlight with no soil to support life. Mosses and their relatives were among the first organisms to spread across these surfaces. Without roots or seeds, they clung to damp rocks, slowly breaking them down and creating the first thin layers of soil. By trapping moisture and accumulating organic matter, they prepared the ground for larger plants and eventually for entire forests and ecosystems. Today, mosses still thrive in extreme environments, on cliffs, rooftops, and frozen tundra. When you see a patch of moss glowing green after rain, you are looking at descendants of the plants that helped transform a lifeless planet into a world rich with life. Certain plants change the shape of their leaves as they grow, a phenomenon known as heteroblasty. Some species produce dramatically different leaf forms at different stages of life. Eucalyptus trees, for example, begin with round juvenile leaves and later develop long, narrow adult leaves. Passionflower vines can produce multiple leaf shapes on the same plant, shifting as they climb and mature. These transformations reflect changing needs, such as capturing light near the ground when young and optimizing efficiency higher in the canopy when older. Changing leaf shapes can also confuse herbivores, making it harder for insects to specialize on a single leaf type. Watching a plant change its leaf identity over time is like seeing adaptation unfold in real time, revealing that even something as familiar as a leaf is never truly fixed. Some trees can store more carbon than entire forests of smaller plants. Giant tropical trees, with their massive trunks and sprawling branches, hold enormous amounts of carbon locked within their wood. A single ancient tree can contain more carbon than thousands of smaller plants combined. These giants often grow for centuries, quietly pulling carbon dioxide from the atmosphere and storing it in their tissues. Losing even one can have outsized impacts on climate and ecosystems. These trees are pillars of biodiversity, supporting insects, birds, mammals, and countless other organisms. Standing beneath such a giant is like standing under a living climate regulator, a towering archive of centuries of captured carbon and ecological history. Plants can detect wind and adjust their growth in response. Wind is not just a force that moves branches and leaves, it is information. When exposed to strong winds, plants often grow shorter and thicker, strengthening their stems for stability. Leaves may change orientation to reduce drag, and stems may bend and reinforce themselves over time. These changes are guided by mechanical signals, tiny pressures and movements that trigger hormonal responses. Over months and years, a plant shapes itself to its environment, becoming a living record of the winds it has faced. What looks like random motion in a breeze is actually a dialogue between plant and atmosphere, with every gust guiding growth and form. In their swaying and bending lies a quiet form of intelligence, a constant conversation with invisible forces. With every gust of wind, plants subtly reshape themselves, thickening stems, shifting leaves, and reinforcing their structures. They are not passive objects in a storm, but responsive beings, adjusting form and structure to endure pressures that never stop. In the gentle arc of a bending stem, there is strategy, memory, and adaptation written into living tissue. Some desert plants send roots deeper than a 10-story building is tall. In landscapes where surface water disappears for months or years, certain plants extend their roots into astonishing depths. Mesquite trees, for example, have been recorded with roots plunging more than 150 feet into the earth, far deeper than a 10-story building reaches into the sky. These roots tap ancient underground aquifers, hidden reservoirs that sustain life in seemingly lifeless deserts. Such depth also anchors the tree firmly, allowing it to withstand fierce storms and shifting sands. When you imagine roots stretching downward through layers of rock and soil into darkness, the desert begins to feel less empty. The visible tree is only a fraction of its true body. Beneath the surface lies a vast hidden system, tirelessly reaching for water and stability, proving that survival often depends on persistence that remains unseen. In the Amazon rainforest, there are palm trees that appear to walk slowly through the forest. The so-called walking palm has fascinated explorers and local communities for generations. It is said to walk by growing new roots toward sources of sunlight while allowing older roots to die away. Over many years, this process can shift the tree's position slightly, sometimes by centimeters, and in rare reports by several meters. Scientists still debate how much actual movement occurs, but the adaptation clearly helps the tree adjust to changing light in the dense forest canopy. The idea of a tree inching its way across the jungle floor sounds like folklore, yet it reflects a deeper truth. Plants are more dynamic than we assume. Through slow and continuous adjustments, they can reposition themselves in response to opportunity. The walking palm reminds us that even organisms rooted to the ground can reach for new horizons, one root at a time. For some plants, fire is not destruction but a beginning. In ecosystems shaped by wildfires, such as pine forests and chaparral landscapes, certain seeds remain dormant until exposed to intense heat or chemicals found in smoke. Fire cracks open tough seed coats or triggers dormant embryos to awaken. The resulting ash bed is rich in nutrients and free from competing vegetation, giving new seedlings a rare chance to thrive. What looks like devastation becomes a powerful reset button for life. When green shoots emerge from blackened soil, it is nature starting over, turning catastrophe into renewal. These plants depend on flames to complete their life cycle, weaving destruction into their survival strategy and reminding us that growth can rise from ashes. Some plants can trap small animals and gain nutrients without being truly carnivorous. While carnivorous plants actively digest prey, other species benefit indirectly from trapped creatures. Certain bromeliads collect rainwater in cup-shaped leaves, forming miniature pools where insects, tadpoles, and even small frogs may fall in and drown. As these organisms decompose, nutrients seep into the water and are absorbed by the plant. Other plants with sticky surfaces can trap insects, not to digest them, but to deter herbivores or gain incidental nutrient benefits. These plants blur the line between passive and predatory, showing that survival strategies exist on a spectrum. Even gentle-looking flowers may quietly profit from the fate of small creatures, revealing a plant world far more opportunistic than it appears. There are trees whose branches grow into living bridges. In the rainforests of India, people have learned to guide the aerial roots of fig trees across streams and ravines. Over decades, these roots intertwine, fuse, and strengthen, forming living bridges capable of supporting human weight. Some of these structures stretch over 100 feet and can last for centuries, growing stronger as the tree continues to live. These bridges are part architecture, part organism, shaped by both human hands and plant biology. Walking across one feels like stepping onto a living entity, a collaboration between nature and culture. They demonstrate that plants are not just passive scenery. They can become integral parts of human infrastructure, living structures woven into daily life. Some plants can photosynthesize through their stems instead of leaves. In harsh desert environments, leaves can be a liability, losing precious water to evaporation. Many desert plants reduce their leaves or lose them entirely, turning their green stems into the primary sites of photosynthesis. Cacti are the most famous examples, using thick, ribbed stems to capture sunlight while conserving moisture. Other plants, such as certain euphorbias, use similar strategies. To us, a cactus may appear bare and leafless, but its entire body functions as a giant leaf, converting sunlight into energy. This adaptation shows how plants reinvent themselves, trading delicate leaves for resilient stems, and proving that life can redesign itself to survive extremes. Bamboo flowering is so rare that it can take more than a century to occur. Bamboo is famous for rapid growth, yet its flowering cycles are among the longest and most mysterious in nature. Many species bloom only once every 60, 80, or even 120 years. When they finally flower, entire populations often bloom simultaneously across vast regions, a synchronization that scientists still struggle to explain. After flowering, most bamboo dies, leaving behind seeds for the next generation. This mass die-off can transform ecosystems, triggering animal population booms and shortages, and affecting human communities that depend on bamboo. The phenomenon feels almost mythical, like a hidden clock ticking for decades before a single grand event. It reminds us that some natural rhythms unfold on timescales far beyond a human lifetime. Some plants grow without soil, thriving directly in air or water. While soil seems essential, many plants have evolved to live without it. Epiphytes such as orchids and air plants grow on trees, absorbing moisture and nutrients from rain and the air. Aquatic plants like water hyacinths float freely, drawing everything they need from water. Inspired by these strategies, humans developed hydroponic systems to grow crops without soil using nutrient-rich water. These plants show that soil is just one option, not a requirement. Life can cling to bark, drift on ponds, or thrive in engineered environments, bending the rules we once thought universal. Flowers can display ultraviolet patterns invisible to human eyes. What looks simple to us may be a glowing map to pollinators. Many flowers have ultraviolet markings called nectar guides that point insects toward pollen and nectar. Bees and other pollinators see these patterns clearly, using them like runways for landing and feeding. Each species has unique UV designs, often hidden until viewed through special filters. A plain white flower to us may blaze with contrast in the vision of a bee. This hidden layer of beauty reveals that nature communicates in wavelengths beyond human perception. Meadows are filled with invisible signals, guiding tiny visitors with luminous patterns we can never see. Certain plants can change the chemistry of the soil around them. Plants do not merely adapt to soil conditions, some actively reshape them. Through their roots and fallen leaves, they release chemicals that alter soil acidity, making it more acidic or alkaline. Pines and oaks, for example, drop litter that lowers soil pH, favoring species adapted to those conditions. Other plants raise soil pH to improve nutrient availability. These changes influence microbes, fungi, insects, and entire plant communities. The soil beneath our feet is not static. It is a living, shifting environment shaped by the plants growing above it, each species quietly engineering its surroundings to suit its needs. Every forest floor and meadow carries a subtle chemical signature, a living fingerprint shaped by the plants that grow there. Through roots, leaves, and invisible compounds released into the soil, vegetation quietly engineers its surroundings. Over years and centuries, these chemical traces accumulate, turning landscapes into archives of plant activity. Beneath every step lies a hidden story of competition, cooperation, and adaptation, written not in words, but in molecules that shape which species thrive and which fade away. Some trees can pump water upward higher than a skyscraper. One of the most astonishing challenges in plant biology is how towering trees lift water from deep roots to leaves hundreds of feet above the ground. In giants like coast redwoods and tall eucalyptus trees, water must travel more than 300 feet upward, surpassing the height of many modern skyscrapers. This process relies on the cohesion of water molecules, which cling together in a continuous column, and the gentle pull of evaporation at the leaves. As water evaporates from tiny pores, it draws more water upward from below, creating a silent, unbroken flow without pumps, muscles, or moving parts. Scientists continue to study the physical limits of this system, yet forests demonstrate its success every day. To stand beneath a towering tree and realize that every leaf at the crown is drinking from the soil far below is to witness a natural engineering marvel more elegant than any machine humanity has built. In the Amazon, seasonal floods turn forests into underwater worlds where fish help pollinate and spread plants. Each year, heavy rains cause the Amazon River to rise, flooding millions of acres of forest. Instead of destroying these ecosystems, the floods give rise to remarkable adaptations. Some trees time their flowering and fruiting to coincide with the flood season, relying on fish to eat fallen fruits and carry the seeds across submerged forests. As fish swim through the flooded canopy, they become seed dispersers, depositing seeds far from the parent tree. The flooded forest becomes a surreal landscape where fish swim between trunks and birds perch above waterlogged roots. This extraordinary partnership shows how plants are woven into complex relationships with animals and rivers. In the Amazon, even fish play a role in forest regeneration, revealing that cooperation in nature often emerges in the most unexpected ways. Some plants use sticky hairs to trap and drown insects. Not all insect-trapping plants are true carnivores that digest prey. Many species grow sticky hairs on their leaves or stems that ensnare insects when they land. Once trapped, the insects may die and decompose, with nutrients washing into the soil and indirectly benefiting the plant. In other cases, the sticky surfaces simply deter herbivores, making the plant unpleasant to eat. Wild tobacco and other plants use these hairs as a defensive barrier, turning trapped insects into a grim protective shield. These strategies blur the line between passive defense and active feeding, showing how plants combine physical traps, chemistry, and chance to survive. What appears to be a delicate hair under sunlight can be a deadly snare, tipping the balance in a quiet battle between plants and insects. Plants can produce toxins powerful enough to become medicines. Many of the world's most important drugs originated as plant defenses. Foxglove produces compounds used to treat heart conditions. Willow bark contains salicin, the natural precursor to aspirin. The rosy periwinkle yielded compounds that revolutionized chemotherapy. These chemicals evolved as poisons or deterrents, protecting plants from being eaten. Yet humans learned to isolate, refine, and repurpose them, transforming toxic molecules into life-saving treatments. This dual nature of plant chemistry, danger and healing intertwined, reveals how thin the boundary can be between poison and cure. Every forest and meadow may contain undiscovered compounds with the potential to change medicine. To the plant, these chemicals are shields. To us, They are possibilities waiting to be understood. Some algae blur the line between plant and animal life. Algae are often grouped with plants, but many species challenge simple classification. Some can photosynthesize like plants while also moving, hunting, or consuming other organisms like animals. Dinoflagellates, for instance, can switch between producing their own food and preying on other microorganisms. Others live inside corals or sea slugs, sharing energy in symbiotic relationships. These organisms occupy a gray zone in evolution, showing that the boundaries between life forms are not fixed. In a single drop of pond water, one can find ancient, versatile beings that defy categories, reminding us that life is more flexible and creative than our labels suggest. Some trees live for thousands of years, older than civilizations. Certain trees have lifespans so long that they predate entire human cultures. Bristlecone pines in the mountains of California have lived for nearly 5,000 years, sprouting long before the pyramids were built. Olive trees, yews, and sequoias also reach astonishing ages, standing as silent witnesses to centuries of change. Their longevity comes from slow growth, dense wood, and the ability to isolate damaged tissues. Each ring in their trunk records a year of history, capturing droughts, fires, and climate shifts. To stand beside such a tree is to feel the presence of deep time, to sense a life that has outlasted empires, languages, and generations of people. These ancient giants remind us that patience can be a powerful survival strategy, and that nature often measures time in millennia rather than moments. Some plants can sense the scent of nearby pollinators and respond. Although plants have no noses, they can detect chemical signals in the air. Certain flowers recognize pheromones released by bees and other pollinators, responding by increasing nectar production or releasing stronger fragrances. Some adjust the timing of their blooms, opening petals precisely when pollinators are active. This sensitivity allows plants to anticipate visitors and maximize their chances of pollination. To us, the idea of a flower smelling seems impossible, yet it reflects the remarkable sensory world of plants. They exist in constant communication with their environment, perceiving signals we rarely notice. As we walk through a garden, flowers may already be adjusting to our presence and to the insects drifting through the air. Some vines slowly strangle entire trees to reach sunlight. Not all vines are harmless climbers. Strangler figs, for example, begin life as tiny seeds dropped onto the branches of another tree. From there, they send roots downward, wrapping tightly around the host trunk. Over decades, these roots thicken and constrict the host, eventually killing it. Once the host dies, the fig stands alone, supported by a lattice of its own roots. This strategy allows the fig to reach sunlight without competing from the forest floor. It is both beautiful and ruthless, a reminder that plants compete fiercely for space and light. Without teeth or claws, they use time and pressure to reshape the forest, slowly claiming territory through patience. The oldest known trees are nearly 5,000 years old. High in the mountains of California grows a bristlecone pine, known as Methuselah, estimated to be almost 5 millennia old. It began growing long before agriculture, writing, or cities existed. Twisted and weathered by centuries of wind and cold, it survives in harsh conditions where few other plants can endure. Thin soils, freezing temperatures, and relentless storms have not ended its life. Instead, these extremes slowed its growth, preserving it for thousands of years. To think that this single tree has witnessed the rise and fall of civilizations is humbling. It stands as a living monument to endurance, a quiet survivor that continues to breathe, grow, and record the passing of time in its rings. Instead of rushing through time, these ancient trees have slowed their growth to an almost imperceptible pace. Each year, they add only the thinnest of rings, layers so fine that decades can pass without noticeable change. Over thousands of years, this slow growth builds wood that is incredibly dense, strong, and resistant to decay. Methuselah stands today as one of the oldest known living beings on Earth, older than empires, older than written history, older than many of humanity's oldest myths. Its existence humbles us, reminding us that life can stretch across time scales far beyond human imagination. While we measure our lives in years and decades, Methuselah measures in millennia, quietly standing as civilizations rise and fall, its patient branches casting shadows across ages. Some plants survive in boiling hot springs, in environments where water bubbles and steams at near boiling temperatures. Certain plants still manage to exist. Algae and mosses have been discovered thriving in geothermal springs, living where most organisms would perish instantly. Their proteins and cellular structures are specially adapted to resist heat, allowing them to photosynthesize in scalding water that shimmers with rising steam. These organisms are studied by scientists searching for clues about how life might exist in extreme environments, from bioengineering on Earth to the possibility of life on distant planets. If life can endure in boiling springs here, it may survive in equally hostile places across the universe. To see delicate green threads weaving through pools of hot water is to witness life's stubborn determination. Even in places that seem utterly uninhabitable, plants find a way to endure, turning heat into habitat and adversity into opportunity. Leaves can trap bubbles of air to help aquatic plants float. For plants living in water, buoyancy can be just as important as roots. Many aquatic species have evolved leaves and tissues that trap air bubbles, creating natural flotation systems. These tiny pockets of air act like life jackets, lifting the plant towards sunlight at the surface. Lotus leaves, for instance, repel water so effectively that bubbles cling to their surface, keeping them dry and buoyant. Other aquatic plants have spongy tissues filled with air spaces that allow entire stems to float effortlessly. What appears to us as a peaceful lily pad drifting on a pond is, in fact, a marvel of biological engineering. Each floating leaf is a living vessel, carefully balanced between sinking and rising, guided by nothing more than trapped air and delicate structure. Nature builds boats not from wood and metal, but from breath and light. Some plants defend themselves with sharp crystals hidden inside their tissues. Beneath the softness of many leaves lies a concealed defense system. Certain plants produce microscopic crystals of calcium oxalate, shaped like tiny needles embedded in their tissues. When an animal bites into these leaves, the crystals pierce the mouth and throat, causing irritation, swelling, and burning pain. Taro, rhubarb, and plants like dumb cane employ this strategy, making them dangerous to eat raw. To the plant, these crystals are armor, silent and invisible until disturbed. The idea that a gentle green leaf can conceal a forest of microscopic daggers is astonishing. Plants may seem defenseless, but their internal structures often form barriers more effective than thorns or bark. Every bite becomes a gamble, reminding herbivores that even the most harmless-looking greenery can strike back in unseen ways. Flowers sometimes bloom in synchrony across vast regions. In some species, blooming is not an individual event, but a coordinated phenomenon spanning entire landscapes. Certain bamboo species, for example, flower simultaneously across hundreds or even thousands of miles, guided by internal biological clocks that may tick for decades. After flowering, the plants produce seeds and then die, resetting the cycle for the next generation. These mass blooms can create sudden surges of food for animals, followed by scarcity when the plants die back. Other plants, such as desert wildflowers, also bloom in synchrony after rare rains, transforming barren land into oceans of color overnight. These events reveal that plants follow rhythms we rarely perceive, rhythms measured not in days or seasons, but in decades and centuries. When the moment arrives, entire landscapes awaken at once, as if the plants themselves have chosen to sing together in a single, breathtaking chorus. Some plants can store a memory of touch, Experiments with sensitive plants like Mimosa pudica suggest that plants can remember being touched. When repeatedly disturbed, their leaves eventually stop folding, as though they have learned the stimulus is harmless. This memory can persist for minutes or even hours before fading. It is not memory in the human sense, but a physiological form of information storage. The plant adjusts its behavior based on past experiences, conserving energy by ignoring unnecessary reactions. This blurs the line between simple reaction and learning, suggesting that intelligence can exist in subtle, biological forms. To imagine a plant holding onto the echo of a touch is remarkable, a quiet trace of experience lingering in green tissue long after the moment has passed. Some trees can regrow entirely from a single fallen branch. For certain species, even damage is an opportunity. When a branch falls to the ground, it can sprout roots and grow into an entirely new tree if conditions are right. Willows, poplars, and banyans are famous for this regenerative ability. In some regions, entire groves form from fallen branches, each one a genetic copy of the original tree. This resilience turns storms and breakage into chances for expansion and renewal. What we see as debris on the forest floor may actually be the beginning of another life. Even broken pieces carry potential, blurring the boundary between destruction and creation. Plants teach us that survival is not always about avoiding damage, but about transforming it into growth. Plants remind us that life on Earth is both fragile and astonishing. From microscopic mosses to towering ancient trees, plants embody resilience, creativity, and patience. They shape the air we breathe, the food we eat, and the landscapes we call home. Yet they remain vulnerable to drought, fire, disease, and human activity. Their survival depends on delicate balances and ingenious strategies, chemical defenses, hidden senses, and remarkable adaptations that allow them to persist in every corner of the planet. When we slow down and truly observe them, we see that they are not passive background scenery, but dynamic architects of the living world. And so we come to the end of our journey through the hidden lives of plants. From roots whispering through soil to trees older than civilizations, we have seen how plants are never truly silent. They are engineers of ecosystems, chemists of survival, and timekeepers of the earth itself. Each leaf, each stem, each bloom and seed carries stories of patience, endurance, and quiet ingenuity. As you drift towards sleep, imagine yourself standing in a forest at night. The air is cool, and the leaves above you move gently in the breeze. Somewhere, a flower unfolds in darkness. A tree lowers its branches, resting until dawn. Beneath the soil, roots reach slowly through the dark, sensing growing alive. Thank you for spending this time with me, exploring the secret world of plants. If you enjoyed this journey, you're welcome to like the video, subscribe to the channel, and join me again for another exploration of science and wonder. But for now, let your mind quiet, your body soften, and your breath slow. The green world holds you in its stillness. Sleep well and dream among the leaves. Good night.